Okay, in the previous lecture, we have studied about the pumping lemma for regular language. Now, in this lecture, we will study about pumping lemma for context free language. Now, what is context free language? I have already discussed in my previous tutorial. In some of the tutorials I have discussed elaborately about the context free language, context sensitive language. So please go through those tutorials, to those video lectures, and after that please refer this one. Okay, so we can write like this way, that a pumping lemma for the context free language is used to prove that a language is not context free. Likewise, you have already studied about the pumping lemma for regular language, where we have used that pumping lemma is used to prove that the language is not regular. Similarly, here we will use this pumping lemma for CFL to prove that a language is not context free. So we can write like this way: pumping lemma for CFL is used to prove that a language is not context free. Okay, so this is the thing. Now first let us give some brief idea about context free language. So context free language. Okay, so it is generated by context free grammar, obviously. Context generated by context free grammar. Okay, and also the set of all CFL, that is context free language, is identical to the set of languages accepted by push down automata. Okay, so CFG is defined by 4 tuples. You already know this. So as G equal to VT, we have studied this in our grammar portion. Okay, VTPS, where you know that V is nothing but set of variables, T is set of terminals, P as is nothing but production rule, and S is start symbol. Okay, so next what we will study that okay, fine. So CFG has production rule of the form A to small a. This is the non-terminal, this is the terminal. Okay, where A equal to V union T star and capital A belongs to V. Okay, now about the definition of context free pumping lemma for context free language. So we can say that if capital L is a context free language, then capital L has a pumping length P such that any string S or W, whatever may be, where modulus of S will be greater than equal to P, may be divided into 5 pieces. S is equal to U, V, X, Y, Z. So already in the previous lecture I told you that in the regular language it is divided into 3 pieces, that is X, Y, Z. Now here in case of context free language we will divide that particular string into 5 pieces, U, V, X, Y, Z. Okay, so these are the two difference between for the regular language and for the context free language. Okay, okay, such that following condition must be true. Must be true. So what are the condition? This is number one condition is U V to the power I X Y to the power I Z. Okay, in L for every I greater than equal to 0. Number 2, V into Y, it should be greater than equal to 0. And number 3, V X Y, it should be less than equal to P. Okay. Now, how to prove this? How to prove this? So, first what you have to do, assume L is context free. Next, it has to be a length, that is pumping length, like this way. Okay, pumping length, suppose say P. And next you can say that all the strings longer than this pumping length can be pumped, that is mod of S greater than equal to P. Okay, next is now find a string S in L such that mod of S greater than equal to P. Next is you must divide S into U, V, X, Y, Z. Next point will be show that U, V to the power I, X, Y to the power I, Z not belongs to L for some this I. Okay, finally then consider the ways that S can be divided into U, V, X, Y, Z. Okay, and also show that none of these, when you divide this X, Y, Z, that particular string, you have to make various type of combinations. We will see in the example. So after that we will understand. So then show that none of these combinations can satisfy, okay, so none of this combination can satisfy we can say all the three, these three ones, okay, all the three pumping condition at the same time, okay. So finally S cannot be pumped so it is nothing but contradiction, okay. Now we will go for one example, okay. So for that we will prove that some a to the power n, b to the power n and c to the power n where n is greater than equal to 0 is your context free, okay. So let us go for that example. So it is given that show that L is equal to a to the, suppose, okay, like this we take a to the power n, b to the power n, c to the power n where n greater than equal to 0 is not context free, okay. So we will consider the two cases, okay. So first one, S is equal to a to the power p, b to the power p, c to the power p. Let us take p is equal to 4 and so S is equal to, you can say, a to the power 4, b to the power 4 and c to the power 4, okay. So this one. Now initially I have done this. Now I will go for the first case 1, okay, case 1. So in case 1 what we will do, that is in the case 1 v and y, okay, v and y, okay, can contain, so when each contain only one type of symbol. I will give you the example, only one type of symbol, okay. So what do you mean that? So let us take this example. So let us take p, this one. So this is your particular string. So let us take like this way, a, how many a? 4a. So 4a, okay, then followed by 4b, b, and then c. Now you have to divide this string into u, v, x, y, z. U, v, you have to divide these strings into u, v, x, y and z, such way that v and y each contain only one tape symbol, okay. So v and y contain either a or b or c, okay. So let us if we consider this case, this condition, so let us divide like this way. Let us say u is this, okay. Now v is combination of only this one. See, v now contains only a, and suppose x, so let us say x is this one, okay, and suppose y can contain only one symbol, so let us say this is only y and this is z, okay. So in this case u and y, v and y, this v and y each contain only one symbol. V contain only a, y contain only c. Now apply this pumping lemma. So what is the pumping lemma? U, v to the power I, x, y to the power I and z. So well, I, let us take I is equal to 2. So what we will get if take I is equal to 2, we will get, if I is equal to 2, we will get a, I is equal to 2 means v square. So there are 2a, so it will be 4a now. X is as it is, b, c, y square, so 2c, so c, and followed by z. Z is normal, so it is again cc. Okay, so this is your v which has been squared, this is your y which has been squared, because I is equal to 2, we take that. So now what we are getting? We are getting how many a's are there? A to the power 6 a's is there, it is b to the power 4 and c is 5, okay, c is 5. Now initially it was all same, the power of each every ABC is same, but here see the power is has changed, different has changed. So the number one condition is not satisfied. Okay, so the number one condition is not satisfied, so we can say that this is not belongs to L. Okay, now we will go for the case 2. So for the case 2, let us see what is case 2. So case 2, in the case 2 we will take like this string that either say V or Y has more, either, okay, not all, so either V and Y has more than one kind of symbols. Okay, so again our string is AA, BB, BB, CC, CC. So has more than one kind of symbol. So let us say this is X, no, so it is U, this is say V. Let us say that V has more than one kind of symbol. So V now consists of 2A and 2B, more than one kind of symbol. Let us consider this as X. Okay, but since U have more than two symbols, so Z will be so Y will be only one kind of symbol. So Y is, let us say it is only B, and Z is nothing but this one, all C. Now our formula is U V to the power I X Y to the power I Z. Let us take I is equal to 2. So now pump it. AA, you pumped V to this V, that is AA BB to 2 times. Now if you pump this 2 times, what you will get? You will get like this way, AABB followed by AABB. Okay, next B, this one BB, and finally CCCC. Now see what we are getting. Initially it was A to the power P, B to the power P, C to the power P, that is after A there is B, after B there is C, and all these are elements are same. Now what we are getting, after A there is a B, but after B there is also again A, and after A there is a B. So this this matching has been breaked. So you cannot say that this is belongs to the original language. So in this way we can say that this is not belongs to L. Hence it is proved. Okay. Okay, in the next we will study another example in the next video. Okay, hope you understand this, that how we should go for this, how should we go for this context free pumping lemma for the context free language. Our main motto is that it is used to prove that the language is not context free. Okay, so you take a string, you have to divide that in 5 parts, U, V, W, X, Y, Z, and you have to pump V part and Y part in you have to pump that 2 part in the same way, where I is equal to 2, 3 or whatever maybe, and after pumping you have to consider, you have to check that language matches with the initial language or not, that is the structure is same or not. So in this case we have studied that we have studied this example and gave the 2 cases, and we found that it is not belongs to that particular initial language, so this is not a context free. Okay, so next we will give another example. Okay, thank you.